Beam bridges. Beam bridges are the simplest structural crossing. A horizontal member resting on supports at each end. That member can be a rolled steel beam, sometimes called a stringer, or a larger steel plate girder fabricated from welded plates instead of a single piece. Most highway overpasses you drive under daily are beam bridges, using concrete girders for grade separation between roads. Box girders are closed structural tubes that use material more efficiently than open beams, though they're more complicated to construct because you're essentially building a hollow rectangle instead of just placing an I-beam. The problem with beam bridges is self-weight. At a certain span distance, the girders become so heavy they can barely support themselves, let alone the roadway and traffic on top. This is why you don't see beam bridges crossing major rivers. Physics gets inconvenient around 250 feet. Truss bridges. One way around the self-weight problem is replacing the solid girder with a truss, an assembly of smaller elements arranged mostly in triangles. Unlike beams, truss members don't experience bending forces. The connections act close enough to hinges that all loads are axial, meaning they run along the length of each member in either compression or tension. This simplifies design because predicting forces in each member is straightforward, and the weight reduction allows trusses to span greater distances than solid beams. Different arrangements have specific names: Pratt, Howe, Warren, bowstring, each suited to different span lengths and loads. A through truss puts the deck on the bottom level, so you drive through the framework, while a deck truss hides structural members below the road. Lenticular truss bridges are particularly photogenic, named because they resemble lenses, which are themselves named because they resemble lentils, which is the kind of naming logic engineers find satisfying. Bailey bridges are temporary trusses designed to be portable and easy to assemble. They were created during World War II and are still used today when bridges fail or close for construction. Basically, the bridge equivalent of a military field hospital. Most covered bridges are timber trusses, with roofs and siding added because wood deteriorates when exposed to weather, and keeping the structural elements trustworthy requires keeping them dry. Trestle bridges. Trestle bridges use a continuous series of short spans with frequent supports rather than one long span. Individual supports are called trestles, but sometimes the whole bridge is called a trestle, which is one of those instances where structural terminology decides to be confusing just because it can. Arch bridges. Arch bridges use curved elements to transfer weight to supports using compression forces alone, instead of beams that bend or trusses experiencing both compression and tension. Many of the oldest bridges used arches because it was the only way to span gaps with available materials, stone and mortar, at the time. The Pont du Gard in France and Roman stone arches across Europe demonstrate arch action that has worked for a couple thousand years, which is better performance than most modern warranties. Modern arches use reinforced concrete or steel, but follow the same principle. The challenge is that arches can't provide support until they're complete, so temporary supports are often required during construction until the arch connects at its apex from both sides. In stone arches, the topmost stone keeps everything standing and is called the keystone because engineers occasionally name things poetically. Deck arch bridges place the arch below the roadway, with vertical supports transferring the deck load down onto the arch. The New River Gorge Bridge in West Virginia is a deck arch where traffic rides on top of the curb. The area between deck and arch is called the spandrel. Open spandrel bridges use columns to transfer loads, while closed spandrel bridges use continuous walls. Through arch bridges have part of the arch extending above the roadway with the deck suspended below. Moon bridges are exaggerated arches, usually for pedestrians over narrow canals where there's insufficient room for long approaches. They're steep enough to require steps or ladders to climb up and back down, which makes them architecturally dramatic and functionally annoying. Tied arch bridges. Compressing an arch creates horizontal forces called thrusts, which means arch bridges usually need strong abutments at each side to withstand those horizontal loads. A tied arch bridge uses a cord connecting both sides of the arch like a bowstring to resist thrust forces internally. This makes tied arches structurally more like trusses than true arches, which provides opportunities for creativity. Network arch bridges use the tied arch design plus crisscrossed suspension cables to support the deck. To distinguish an arch from a tied arch visually, look at the supports. If the end of each arch sits on a spindly pier or some other structure that seems insubstantial against horizontal forces, they're probably tied together and it's not a true arch. Rigid frame bridges. Rigid frame bridges integrate the superstructure and substructure, the deck, supports, and everything else, into a single monolithic unit. They don't have to be arched, but many are, creating a continuous structural system that transfers bending moments, axial forces, and shear forces throughout. Cantilever bridges. Cantilever bridges use beams or trusses that project horizontally. balancing most of the structure's weight above the supports rather than in the center of the span. This technique is effective enough that the Forth Bridge crossing the Firth of Forth in Scotland took the title of longest span in the world, away from the Brooklyn Bridge in 1890, and held it for decades. The famous photograph demonstrating this bridge's principle shows how two central piers bear compression loads, while the outermost supports are anchors providing balancing force for each arm, allowing a suspended load in the middle. The Quebec Bridge in Canada is another well-known cantilever truss, famous for both its size and its catastrophic early collapse. A reminder that engineering innovation sometimes involves spectacular failures before success. Cable-stayed bridges. Cable-stayed bridges support the deck from above through diagonal cables, called stays, attached to tall towers or spars. The cables form fan patterns, giving this bridge type its distinctive appearance. Depending on span requirements, cable-stayed bridges can have one central tower or more, and their simplicity allows for a wide variety of configurations, producing some dramatic and often asymmetric shapes. The cables at towers can be arranged in parallel patterns resembling harp strings, fan configurations where cables converge at a single point at the top, or radial and mixed layouts. Tower designs include single-column towers for minimalist aesthetics, A-shaped towers that angle toward each other providing stability for long spans like the Arthur Ravenel Jr. Bridge in South Carolina, H-shaped towers combining portal frames on the bottom with double columns on top as seen in the Vasco da Gama Bridge in Portugal, and inverted Y designs like the Pont de Normandie in France. Real-world examples include the Millau Viaduct in France with single-column towers, the Øresund Bridge between Denmark and Sweden with double arrangements, and the Sunshine Skyway Bridge in Florida. The Ruski Bridge in Russia and Bandra-Worli Sea link in India demonstrate how cable-stayed designs handle medium spans, typically ranging from 200 to 1,000 meters. Cable-stayed cradle system bridges carry strands within stays from deck to deck as continuous elements, eliminating anchorages in the pylons. Each epoxy-coated steel strand runs inside a steel tube within cradles, allowing individual strand removal, inspection, and replacement, basically making bridge maintenance slightly less nightmarish. The Penobscot Narrows Bridge and Veterans Glass City Skyway were the first examples of this system. Extradosed bridges. For shorter spans, you can combine benefits of cable-stayed structures with girders to get an extradosed bridge. Imagine a concrete girder bridge using internal tendons to keep concrete in compression. Then pull those tendons out of the girder and attach them to a short tower. Rather than holding the deck up vertically like cable-stayed bridges, they act more horizontally to hold girders in compression, providing stiffness needed to support the deck. It's a relatively new concept compared to most other designs, suitable for 100 to 250 meter spans. But there are quite a few examples across the globe. Suspension bridges, where cable-stayed bridges attach the deck directly to each tower. Suspension bridges use cables or chains to dangle the deck below. In simple suspension bridges, the cables follow the deck's curve, your classic rope bridge over a ravine. They're not very stiff or strong, so simple suspension bridges are usually only for pedestrians, which is probably for the best since most people don't enjoy their roadways swaying. Stressed ribbon bridges integrate cables into the deck, pulling it into compression to provide stiffness and stability, so it doesn't sway and bounce. This design is primarily used for smaller pedestrian bridges because it can't span long distances and the deck sags in the middle. Lake Hodges Pedestrian Bridge in California, at 303 meters, is the world's longest stressed ribbon bridge. Suspended deck bridges are the design most associated with suspension bridges, featuring the longest spans in the world. Massive main cables or chains dangle the road deck below with vertical hangers. Towers on either side prop up the main cables, transferring most of the bridge's weight into the foundation through these towers. The rest transfers into the bridge's abutments through immense anchorages, keeping cables from pulling out of the ground. The Golden Gate Bridge in San Francisco, Akashi Kaikyo Bridge in Japan, the world's longest suspension bridge, and Brooklyn Bridge in New York are iconic examples. The 1915 Sanacal Bridge in Turkey and Humber Bridge in England demonstrate how suspension designs handle spans exceeding 1,000 meters. Self-anchored suspension bridges connect main cables to the deck on either side, compressing it to resist tension forces instead of using ground anchorages. Because suspension bridges are so slender and lightweight, most require stiffening with girders or trusses along the deck to reduce movement from wind and traffic loads. These bridges are expensive to build and maintain, so they're really only used when no other structure will suffice, but you can hardly look at one without being impressed. Movable bridges. Bridges must support vehicles and people crossing the deck, but often must accommodate boats and ships passing underneath. If it's not feasible to build the bridge and approach is high enough, another option is having it get out of the way when ships need to pass. Movable bridges come in all shapes and sizes, and many people call them drawbridges after their medieval castle moat brethren. Bascule bridges are hinged so the deck can rotate upward, offering unlimited vertical clearance once open, though they're susceptible to wind forces in that position. Swing bridges rotate horizontally about a vertical central pivot pier, so ships can pass on either side, functioning as two-span continuous beams when closed and as cantilevers when open. Vertical lift bridges raise the entire deck upward while keeping it horizontal like a table, with maximum raising height limited by tower height but minimizing traffic delays by raising only to minimum necessary clearance for vessels. Transporter bridges are particularly unusual. They have a small length of deck shuttled back and forth across a river on overhead cables, designed for locations where long approach ramps or traditional high-level bridges are impractical. These specialized structures can only carry limited loads and were popular in early 20th century Europe, but saw declining use following automobile proliferation. Every movable bridge is unique and customized for specific locations, so there are some truly interesting structures if you keep an eye out. Floating bridges. Sometimes there's no need for ship passage or space below, and in that case you can just float the bridge on the water. Floating bridges use buoyant supports, often hollow concrete structures, as pontoons with pumps inside to prevent them from filling with water and sinking, eliminating the need for foundations. These are used in military applications and some permanent installations, though they present interesting engineering challenges, including accommodation for water traffic, mooring systems with cables and anchors to prevent overstressing and dangerous movements, and retractable or elevated spans. The pedestrian bridge at Fort de Rouveure in the Netherlands has its deck below water level, giving it the nickname Moses Bridge. Submerged floating tunnels, also called Archimedes bridges, float underwater, held in place by cables anchored to the seabed or surface pontoons, positioned deep enough to avoid water traffic while remaining in manageable pressure depths, typically 20 to 50 meters. This emerging technology combines floating structure principles with tunnel functionality, proposed for extremely deep water crossings in Norway and elsewhere. Low water crossings. If space or funding is really tight, one option to span a small stream is a low water crossing. Unlike bridges built above typical flood levels, low water crossings are designed to be submerged when water levels rise. They're most common in areas prone to flash floods, where runoff in streams rises and falls quickly, with crossings ideally inaccessible only a few times per year during heavy rainstorms. Low water crossings have disadvantages. They can block fish passage like a dam, and there's safety. A significant proportion of flood-related fatalities occur when someone tries driving through water overtopping a roadway. Water is heavy, and it takes only a small but swift flow to push a vehicle down into a river, which means resources saved by avoiding the cost of a higher bridge are often spent erecting barricades during storms, installing automatic flood warning systems, and running advertisement campaigns encouraging motorists never to drive through water overtopping a roadway. Viaducts and special classifications. Viaducts aren't so much a specific bridge type, but really about length. Bridges spanning wide valleys need multiple intermediate supports, so a viaduct is just a long bridge with multiple spans, mostly above land. There's not much agreement on what is one and what isn't. Some are singular impressive structures, but many modern cities have viaducts that are, although equally amazing from an engineering standpoint, a little less beautiful, so you're more likely to hear them called elevated expressways. Aqueducts are bridges carrying water rather than vehicular traffic, spanning valleys on multiple arches or piers with watertight channels, managing flow requirements distinctly from road bridges. Causeway bridges provide long crossings over water or marshland using continuous or nearly continuous fills with multiple support points. Without listing every bridge, there's no true way to list every type of bridge. There's too much nuance, creativity, and mixing and matching designs. The Phyllis J. Tilley Bridge in Fort Worth combines an arch and stressed ribbons. The Third Millennium Bridge in Spain uses a concrete tied arch with suspension cables, holding up a deck stiffened with box girders. The Yavuz Sultan Selim Bridge in Turkey combines cable-stayed and suspension design. In parts of India and Indonesia, living tree roots are used as simple suspension bridges over rivers. There are bridges for pipelines, bridges for water, bridges for animals. Once you understand the basics, you can start to puzzle out the more interesting details, and eventually you'll see the Akashi Kaikyo Bridge on a calendar and recognize it as a twin-hinged, three-span, continuous, stiffened, truss girder suspension bridge with a double tower system. Subscribe to learn about more city infrastructure that we can't live without, but know little about.